Hello dear students, welcome to this video lecture on Applied Mathematics 5th semester of University of Mysore, session number 19. In this video lecture we shall see Fourier series of the function which is defined in the interval minus L to plus L. Before going to the Fourier series expansion, you recall what are the conditions that a function has to satisfy in order to expand it in the form of Fourier series. That is, you have studied the Dirichlet's conditions. These are the conditions that a function has to satisfy in order to expand that in the form of Fourier series. And also, in order to solve the problems, you should know the properties of definite integrals and also the techniques of integration. Fourier series expansion in the interval minus L to plus L. Suppose the function is periodic. You see, in order to expand the given function in terms of Fourier series, first of all the function should be periodic one. If the function is periodic and it is defined in some interval, say minus L to L, where L is any positive number, then the Fourier series expansion of the function f of x is given by this formula. It is important formula, you should remember this one. F of x is equal to a naught by 2 plus sigma n is equal to 1 to infinity a n cos n pi x by L plus sigma n is equal to 1 to infinity b n sin n pi x by L. This is the Fourier series expansion of the given function f of x, which is defined in the interval minus L to L, where L is any positive number which is called as period of the given function. And in the formula, you note that a naught, a n, b n, these are the constants which are called as the Fourier constants, or sometimes we are also call them as Euler's constants. And we have derived the formula for these three constants in your previous video lectures. Now let us see what are all the formulas for these Fourier constants. The formula for a naught is given by 1 by L times integral minus L to plus L f of x dx, and a n is given by 1 by L times integral minus L to plus L f of x into cos n pi x by L dx, and bn is given by 1 by L times integral minus L to plus L f of x sin n pi x by L into dx. Using these three formulas, we are going to find the Fourier constants a naught, a n and b n. Once if we find these constant values, then we substitute these constant values in this equation to get the Fourier series expansion of the given function f of x, which is defined in the arbitrary interval minus L to plus L. Now let us look into some problems in the next slides. Problems on Fourier series. First problem, find the Fourier series of the function f of x is equal to, it is defined in the interval minus 2 to plus 2, and the function is defined to be 0 when x lies between minus 2 to 0, and the function is defined to be 1 when x lies between 0 to 2. If the function is defined like this, then we have to find out the Fourier series expansion of this given function. Solution goes like this. First of all, you write down what is the interval given here. Here the given interval is minus 2 to plus 2. Therefore, length of the interval is given by final value minus initial value. Final value is 2, minus initial value is minus 2, therefore length of this interval is 4 and it is denoted by 2L. Length of the interval is denoted by 2L. So we get 2L is equal to 4, which implies L is equal to 2, which is called as the period of the given function. So L is equal to 2 is the period of this function. So whenever the problem is given to you to expand the function as a Fourier series, first of all what you have to do is you have to identify what is the period of that given function, that is L value. After finding the L value, next you go to find the values of the Fourier constants a0, an and bn. Now let us see how to find the Fourier constants a0, an and bn. Write down the formula to find a0. a0 is equal to 1 by 2 times integral minus 2 to plus 2. You remember the formula for a0 is equal to 1 by L times integral minus L to plus L f of x dx. In place of L, I am substituting 2. So we get 1 by 2 times integral minus 2 to plus 2 f of x dx. Now, in order to evaluate this integral, use the property of definite integrals. You split integral minus 2 to 0 as according to the function defined. The function defined in the interval minus 2 to 0 as 0 and the function defined in 0 to 2 as 1. You split this integral minus 2 to plus 2 as minus 2 to 0 and 0 to 2. This is the one of the property of definite integrals. So I am splitting the integral minus 2 to plus 2 like this 1 by 2 constant integral minus 2 to 0 f of x dx plus integral 0 to 2 f of x dx. Now in the interval minus 2 to 0, the functional value is 0. It is given 0 to in minus 2 to 0, the function is defined to be 0, and in 0 to 2, the function is defined to be 1. Substitute the corresponding values of the function defined in the respective intervals. So 1 by 2 times integral minus 2 to 0, in this interval functional value is 0, plus integral 0 to 2 f of x in this interval is 1 into dx. Anyhow, this value goes off because functional value is 0. So we get 1 by 2 times integral 0 to 2 1 dx. So if I integrate this value is 0. Integral of 1 dx is x between 0 to 2. So we get 1 by 2 times upper limit 2 minus lower limit 0. 2 minus 0 is 2. So we get 1 by 2 into 2. Therefore the value of a0 is 1. So this is how we have to find the value of the first Fourier constant a0. Now in the next slide we shall see how to find the second Fourier constant an. Yeah, this is the second Fourier constant an. After substituting in place of L as 2, we get this 1 by 2 times integral minus 2 to plus 2 minus L to plus L, where L is 2 here. Therefore we get integral minus 2 to plus 2 f of x cos n pi x by L is 2 into dx. Again you split this integral into sum of two integrals like this. 1 by 2 times integral minus 2 to 0 f of x into cos n pi x by 2 dx plus 1 by 2 times integral 0 to 2 f of x into cos n pi x by 2 dx using the property of definite integrals. Now you substitute the functional value in the respective interval. In minus 2 to 0, the functional value is 0. Therefore, this first integral entirely goes off because the functional value is 0. We get only the second integral. Okay, so first integral goes off, it is 0. We get only the second integral, it is 1 by 2 times integral 0 to 2. In that interval, functional value f of x is 1. I am substituting here into cos n pi x by 2 dx. So finally we get 1 by 2 times integral 0 to 2 cos n pi x by 2 dx. Now in the next step we have to integrate the given integrand. So we get 1 by 2 times integrate cos n pi x by 2. Integral of cos n pi x by 2 is sin n pi x by 2 divided by the constant n pi by 2. The constant n pi by 2. So you remember we get 1 by n pi by 2, 2 gets cancelled, we left with 1 by n pi. Here 2 and this 2 gets cancelled, we get 1 by n pi as constant. We can take it that outside to get the next step like this, 1 by n pi into apply the limits of integration for x now. So upper limit, put x is equal to 2 here. If I put x is equal to 0, mean 2 gets cancelled, we get upper limit as sin n pi. Okay, and do you remember what is the value of sin n pi? Remember, sin n pi is 0 for all n. Whatever may be the value of n, sin n pi is 0. Therefore upper integral value is 0. Now put lower integral, lower limit. So put x is equal to 0, we get sin n pi into 0 by 2. So finally we get sin 0. Sin 0 is 0. Therefore upper limit is also 0, lower limit is also 0. That's why we get 0 here. Okay, so 1 by n pi into 0, that is equal to 0. Therefore for this problem the value of second Fourier constant an is equal to 0. Now let us find the third Fourier constant Bn. So Bn is equal to 1 by 2 times integral minus 2 to plus 2 f of x into sin n pi x by 2 dx. So now split the integral like this. Okay, now in place of f of x in the first integral you put 0, therefore this term entirely goes off. Therefore we get only the second term where the functional value f of x is 1 here. So we get this 1 by 2 times integral 0 to 2 f of x is 1 into sin n pi x by 2 dx. Okay, in the next step, if 1 by 2 is constant, you integrate sin n pi x by 2. Integral of sin is minus cos, therefore we get minus cos n pi x by 2 divided by this n pi x by 2, where n pi by 2 is constant, so we get n pi by 2 here. So anyhow this 2 and this 2 gets cancelled and we get 1 by n pi along with this minus. So therefore we get here minus 1 by n pi. Now put limits of integration. Put x is equal to 2, upper limit. So we get cos n pi into 2 divided by 2. 2 gets cancelled. So therefore we get upper limit as cos n pi. Upper limit as cos n pi, and note that cos n pi is equal to minus 1 to the power of n. Its value is cos n pi is either plus 1 or minus 1 according as n is even or odd. So therefore we get cos n pi, we get when I apply x is equal to 2 the upper limit, so we get cos n pi, its value is minus 1 to the power n, minus when I put lower limit x is equal to 0 here, we get cos 0, and note that cos 0 is equal to 1. That's what we get. Now multiply this minus inside the bracket to get 1 by n pi into, you see, minus 1 to the power of n into minus 1. Using theory of indices, we can write that as minus 1 to the power of n plus 1. And then minus 1 into minus 1 is plus 1. So this is what we get, and this is the value of the second Fourier constant Bn. So we have determined all the Fourier constant values a0, an and bn. a0 is 1, an is 0 and bn is given by 1 by n pi minus 1 to the power of n plus 1 plus 1. After finding all the Fourier constants, you write down the formula, substitute the values of a0, an and bn, and you will get the Fourier series expansion of the given function. Let us see that in the next slide. Okay, the Fourier series of the given function is, so this is the formula you should remember. F of x is equal to a0 by 2 plus sigma n is equal to 1 to infinity a n cos n pi x by l plus sigma n is equal to 1 to infinity b n sin n pi x by l. Substitute the constant values a0, an and bn. Remember, a0 we have determined it as 1 and an is 0, therefore this middle term goes off, and bn is, we have determined it as 1 by n pi times minus 1 to the power of n plus 1 plus 1. Substituting those values, we are going to get this. a0 is 1, this a0 is 1, so we get 1 by 2 plus, and middle term goes off because an is 0, therefore we get 0 here, plus in the last term sigma n is equal to 1 to infinity. I am substituting for bn, it is 1 by n pi times minus 1 to the power of n plus 1 plus 1 into sin n pi x by l means the period it is 2. Okay, yeah, so now I am simplifying this further, this 1 by 2 as it is, and I am not writing this 0. So now in the last we are going to expand the summation, go on putting n is equal to 1, 2, 3 and so on. Observe what you are going to get. See, if I put n is equal to 1 here, so we get minus 1 square. What is the value of minus 1 square? Minus 1 square is plus 1. Okay, therefore we get plus 1, we get 2. Am I right? 1 plus 1 is 2 when n is equal to 1. So we get 2 divided by 1 pi, we get 2 divided by 1 pi, of course. See, if I put n is equal to say 2, we get minus 1 power 3. Am I right? Minus 1 cube. But what is minus 1 cube? Minus 1 cube is minus 1. So minus 1 plus 1 here gets cancelled. We get this entire term 0. If I put n is equal to say 3, we get minus 1 power 4. It is plus 1 plus 1 plus 1 becomes 2. If I put n is equal to say 4, we get minus 1, this entire term goes off. So therefore what we can conclude is, when n is odd, you will get 2 times here. When n is even, you will get 0 here. Okay, so therefore for even terms, this terms goes off. For odd terms, you are going to get 2 here. For odd terms, we are going to get 2 here. Therefore we write the 2 by pi outside. 2 by pi outside. This is the term we get for n is equal to 1. This is the term we get for n is equal to 1. You see, 1 by 1 into sine 1 pi x by 2. That is pi x by 2. This is the first term we get for n is equal to 1. And remember, for n is equal to 2, this term goes off. We won't get any term for n is equal to 2 for even term. Next, when n is equal to 3, you will get 2 here. That 2 by pi we are taking that outside. Okay, and now for n is equal to 3, we get 1 by 3. Pi is taken outside here. So we get 1 by 3 into sine 3 pi x by 2. This is the term we get for n is equal to 3, and for n is equal to 4 we won't get any term, we get 0 here, and this is the term we get for n is equal to 5 and so on. Remember, these are all the terms that corresponds to when n is odd number. Remember that. Okay, so this is what is the Fourier series expansion of the given function. Okay, now let us see the second problem on this. Find the Fourier series for the function f of x is equal to 1 minus x square when x lies between minus 1 to plus 1. Here the function is defined in the interval -1 to +1. So therefore length of the interval is final value minus initial value, that is 2. Therefore 2l is equal to 2 implies l is equal to 1. Therefore the period of the given function is l is equal to 1. Now write down the formula for a0, 1 to 1, this 1 by 1, that is 1 by l, where l is 1 here, integral -1 to +1 f of x dx. So substitute for f of x, it is 1 minus x square, integrate term by term, integral of 1 is x and minus integral of x square is x cube by 3, and apply the limits of integration, upper and lower limit. So we are going to get 4 by 3. You simplify that yourself, we get the first Fourier constant a0 to be equal to 4 by 3 after applying the upper and lower limit. Now let us see the second Fourier constant in the next slide. The second Fourier constant is given by an is equal to 1 by 1 integral -1 to 1 minus x square into cos n pi x into dx. So we have to integrate this by parts, or we have to integrate this by Leibniz rule and all that. So you are going to get this. So I am integrating this in a single line like this. Probably you might have know the method of integrating the product of two functions like this. See, you first decide what is the first function and what is the second function. So here I am choosing first function as 1 minus x square and cos n pi x as the second function. Okay, the first function is 1 minus x square. How to choose the first function? Remember, the first function has to be chosen in such a way that if we go on differentiating successively that one, you should get 0 at one stage. So if I differentiate 1 minus x square successively, at the third stage you are going to get 0. That function has to be chosen as first function. Suppose if I take cos n pi x as first function, you will never get 0 by successively differentiating that. Derivative of cos is sine, again differentiate we get cos, again differentiate we get sine, and so on. Therefore you don't take cos as first function, you take 1 minus x square as first function and remaining cos n pi x as second function. The method of integrating the product of these two is like this. You keep the first function as it is, 1 minus x square, and integrate the second function. Integral of cos n pi x is sin n pi x divided by n pi, this constant. Next you put minus sign. You differentiate the first function once. Derivative of 1 minus x square is minus 2x. Next again integrate this one. Integral of sin n pi x by n pi is minus, integral of sin is minus cos n pi x divided by n pi into n pi we get. So that is n square pi square. Next we get plus sign. We are going to get alternatively plus and minus signs. So here we have plus sign, here we have minus sign, therefore next we have plus sign. And next you differentiate minus 2x again, so we get minus 2, and you integrate minus cos n pi x by n square pi square. So minus is here, integral of cos is sin n pi x divided by n square pi square into n pi we get, so we get n cube pi cube. Suppose next step what we get is minus, if I differentiate minus 2 we get 0, therefore we won't write the remaining steps. Okay, between the limits -1 to +1. So apply the limits of integration. Now see, when I put upper limit for x, that is 1, here I get sin n pi 1, that is n pi, sin n pi. Of course if I put x is equal to 1 here, you will get 1 square is 1, 1 minus 1 is 0. This term goes off if I put n is equal to 1. Am I right? Next, if I put n is equal, n, not n, x. If I put x is equal to 1 here, see, minus minus plus, plus into minus minus here. So we get 2 into 1 is 2, minus 2 cos n pi divided by n square pi square. We get here one term, that term is minus 2 cos n pi divided by n square pi square. Suppose if I put x is equal to 1 here, we get sin n pi, and as I said earlier, sin n pi is 0. So therefore, when I put upper limit for x is equal to 1, this goes off and the first term also goes off. We get the term only in the middle. The term is equal to minus 2 cos n pi divided by n square pi square. This is what is the upper limit. Next we get minus lower limit. You put lower limit x is equal to minus 1, we get again this 0. Okay, and it is also 0. We get sin minus n pi, we get it is also 0. Therefore we won't get the terms in the first and last. Okay, so next you put x is equal to minus 1 here. So therefore here we get again, after simplifying all the signs, we are going to get minus 2 cos n pi divided by n square pi square. Minus into minus plus, plus into minus minus, minus into minus plus, and lower limit minus we get minus. Therefore minus 2 cos n pi by n square pi square. Upper limit we have minus 2 cos n pi by n square pi square, minus lower limit is also minus 2 cos n square pi square. Both get added up, we get minus 4 cos n pi by n square pi square. And note that cos n pi is minus 1 to the power of n. So we get minus 4 minus 1 to the power of n divided by n square pi square. This is what is the Fourier constant an. And remember, this function is even. For even functions, this third Fourier constant Bn is equal to 0. You might have all know this condition. So for odd function, we are going to get the first and second Fourier constants are zeros, a0 and an. For even function, the third Fourier constant is 0. Therefore, you don't calculate the value of Bn. Straight away you can write Bn is equal to 0 as the given function is an even function. So Bn is 0. So we have determined all the Fourier constants a0, an and Bn. Substitute them in the given form. Yeah, the Fourier expansion of the given function is, this is the Fourier expansion of the given function. Substituting the values, so we get, so the value of a0 is 4 by 3, you know, 4 by 3 by 2 is 2 ones are 2 twos are, so we get 2 by 3 here, plus n is equal to 1 to infinity. An value is minus 4 into minus 1 to the power of n square pi square cos n pi x, and we won't get any terms from the last because Bn is 0. So now this is 2 by 3, and here we get minus, you multiply that with this. So we get minus 1 to the power of n into minus 1 here. So we get minus 1 to the power of n plus 1. And 4 by pi square is constant and it will nothing to do with sigma. Therefore, you take it outside. 4 by pi square, n is equal to 1 to infinity. Minus 1 to the power of n plus 1. N square into cos n pi x. So now you go on putting n is equal to 1, 2, 3, etc. So we get 2 by 3 plus 4 by pi square. When n is equal to 1 here, we get minus 1 square and it is positive. So positive divided by 1 square is 1. So cos 1 pi x, that is cos pi x. This is the first term we get. When n is equal to 2, we get minus 1 power 3. Minus 1 power 3 is minus 1 divided by 2 square into cos 2 pi x. When n is equal to say 3, 2, we are going to get this term. We get for n is equal to 1 this term, for n is equal to 2 we get this term, for n is equal to 3 we get this term. So for odd numbers or odd integers we get positive values, and for even numbers we get negative terms like this. This is what is the of the given function. So these are all the exercise problems that you may solve yourself. Thank you.